Okay, if you're ready, we can start. Hello, everyone. Thank you for joining us today in another machine learning launch seminar at Vanderbilt University. We are very excited to have Kayhan Batmanghelidj as our speaker today. Kayhan is an assistant professor at the University of Pittsburgh. He received his PhD from UPenn under the supervision of professors Ben Tasker and Christos Davatsikas. He spent 3 years as a postdoc in CSAIL at MIT, working with Professor Paulina Goland. And Kayhan's research is at the intersection of medical vision, machine learning, and bioinformatics. His group develops machine learning methods that address the interesting challenges of AI in medicine, including explainability, learning with limited and weak data, and integrating medical image data with other biomedical data modalities. Kayhan's research is supported by awards from NIH, NSF, and other industry projects. I'm really glad that we have Kayhan as a speaker today. And Kayhan, with that, the stage is yours.
Thank you very much. Thank you very much for the invitation, Sohail and Tyler. It's an honor to be here. I'm excited to talk about the research of my lab in the intersection of machine learning and healthcare application, where we view the method development and insight from clinical domain as a two-way bridge that inform each other, hence this image of Andrew Warhol Bridge in Pittsburgh. So healthcare industry is arriving in a new era that AI is increasingly adopted by clinical workflow. So one of the driving forces that brought us to this age is increasing the cost of the healthcare. This curve shows the per capita spending from 1970 that even after correcting for inflation has experienced six-fold increase. Adoption of the AI for medical application, healthcare application, is going to have impact for clinicians and healthcare system by making them more efficient, and also for patients in terms of receiving more personalized healthcare. So when we are trying to about the future of AI in medicine, many people would like to compare it with autopilot in a self-driving car, more specifically due to importance, also need for safety and trustworthiness in the system. In my opinion, AI medicine is less like a self-driving car and more like a semi-autopilot in a commercial airplane. And the difference between them, the ultimate goal of a self-driving car is to remove human, while in an autopilot system, we have the pilot in the loop. And I believe that many of the important challenges that some of which I'm going to explain in the following slides, going to represent itself in this analogy of having human in the loop, including efficiency in the training, explainability, incorporating underlying physics of the system, and understanding causality. So if we consider the application of ML in healthcare as a spectrum, that one end of that is bedside practice, the other end is medical domain, ML has found application almost everywhere, from helping radiologists to read the images faster, to finding the optimal embryo for IVF that reduce the chance of miscarriage, all the way to the news that you have heard about predicting the secondary structure of the protein that is a stepping stone for drug development. So throughout this spectrum, there are many challenges and, of course, opportunities for research. So in my opinion, there are 4 challenges of application of machine learning in healthcare. So one of them is multimodality. Decision-making clinic is always multimodal. So doctors look into an array of information from the images, lab test, record of the patient to make a decision. The challenge is how to construct a model that consumes this information in an efficient manner. Explainability is another challenge. It's important. We are increasingly using more and more complex models. It is important to explain the decision of these black boxes to clinicians, not only to gain a trust, but also to ensure that our model does not latch in spurious features. It is important to take maximum advantage of this expensive data. So data efficiency is another challenge in application of ML medicine by incorporating knowledge into this information and so on and so forth. And finally, if you want to use it for medical research, which is toward the end of this spectrum, we have to go beyond prediction toward understanding causal relationship. My group has contributed to many of these in multiple research, but today I'm going to talk about two of the project, which is about data efficiency in learning and inference and explainability. So let's get started. In the first part of the talk, I'm going to talk about how we can gain data efficiency in the context of a specific disease using self-supervised approach, and then how we can use this idea for statistical inference. This is the project done in collaboration with my colleagues in CMU, Kung Zhang, and my former postdoc, Ming Gong, who's right now faculty in Australia in the stat department, and two of my students, Lee Sun and KU. So let me explain, give you a little bit context about the underlying disease that we are interested in. This disease is called chronic obstructive pulmonary disease, COPD, which is one of the leading causes of death in the US and also worldwide. It's ranked sometimes number 3 and 5, depends on the sources. So there are multiple symptoms associated with the disease. Shortness of the breath and cough is another one. And there are multiple risk factors, including smoking, pollution, but there is also important genetic and environmental risk associated with the COPD. So the way that the disease is diagnosed is through a machine called the spirometer. A patient is asked to exhale air in his lung through a device called the spirometer, and the spirometer measures amount and the speed of the air that the time that it takes for the lung to empty all of the air. So there are several processes involved in this disease, COPD. Two of the major one is destruction of the air sacs, so-called emphysema, and the second one is these airways that become inflamed, and then obstruct the flow of the air. But these spirometers is an aggregate measure that cannot dissect or disentangle the effect of multiple processes. And this is why computer tomography, CT imaging, is increasingly used for diagnosis and also characterization of the disease, because it directly measures the effect of the disease on the anatomy. So if I put the aims of this first part of my talk into multiple aims, the first aim is that, is it possible that we can come up with a data-driven approach that characterize the progression of the disease in a comprehensive manner beyond the classical metrics of the features that we extract from the images? And the second one is that we want to relate this information that we extract from the images to other biological measures, for example, the measurement that we have from the blood or genetic measurement, etc. So perhaps one of the first things that comes to my mind, to our minds as a computer scientist or people who are interested in machine learning, is that why not using our method, for example, a deep learning approach that, for example, learn some features from the images that predict the spirometry characteristic. And in fact, you can do that. In the paper that we published a couple of years ago, we showed that you can construct such a method relatively easily, of course, accounting for the context, and it performs much better than previously proposed method and classical metric of disease severity in terms of predicting these specific metrics of disease severity. Here on the y-axis, I'm showing you R square of forced expiratory volume, so-called FEV1, which is one of the metrics of disease severity. And on the blue bars is the method that is using deep learning approach, and the other methods are classical metrics that do not use deep learning, or very classical metric that is used clinically, and it basically shows how predictive it is with respect to the measuring the severity of the disease. But now the question is that this disease is quite complicated disease. Respiratory measurements are only one of the factors. Question is that how much this information that we have extracted from images are generalizable to other metrics of the disease severity. So one experiment that comes to our mind is that, well, we have trained this model. Let's look into the pre-optimum layer features and see if we can use these to other metrics of the disease severity. We looked into another metric of disease severity that is about shortness of the breath. So it's called MMRC. The name is not that important. It's basically, it's about shortness of the breath, but it's not done through the spirometry test. So we said that, okay, so what if we perform this experiment? We train this model, we freeze the network, and we use the features in a new, let's say, linear regression to predict this MMRC. We call it indirect approach. And we can also retrain this model with respect to MMRC. If the features we are extracting is generalizable enough, there should not be a big gap. And unfortunately, we see that the gap between these two are relatively large, which suggests that the the features that are extracted from one metric of the disease are not necessarily performing well for other metrics of the disease, no matter how relevant they are. And this was basically brought us back to the general aims that is it possible that we can extract generic features that can that are predictive of many metrics of the disease severity in an unsupervised fashion or with minimum supervision? Perhaps talking to this audience, that many of audience I'm presuming are from computer science or computer science department, probably one of the first things that comes to mind would be self-supervised learning. So without going too much detail, I'm sure many of the people in the audience are familiar with the general idea of a self-supervised learning. But unlike basically supervised learning, self-supervised learning are not trained for one specific task, but rather the goal is to learn a representation that can distinguish each instance from the others, and with the hope that these features that we extract are generic enough that can be applied in a diverse application. There are multiple variants of the self-supervised learning. Probably one of the most popular, or the most popular one, is so-called contrastive learning, that you are given an image, let's say image of a dog. You can apply a set of transformation that does not change the semantic, for example, changing the color, rotation, etc., and we call it positive set. And the random draw from your data set, which is the negative set. And the goal is to train a feature extractor and an encoder, where the similarity between two elements in a positive set are closer to each other than similarity from element of a positive and a negative set. Now, the question is that, okay, so this is the general idea of self-supervised learning. There are multiple ways to learn such a network. The most common ones probably Info and CE. What would happen if you apply this method on the medical images? So, here we have, let's say, a patch from a region of the lung, and we can apply a set of transformation that does not change important features or semantic in the image, for example, rotation or change of the contrast a little bit, and that constitute our positive set. And a negative set would be a random draw of the patch from the other patient on other locations. Unfortunately, if you apply this method and try to learn a self-supervised learning, the model will learn to cheat and use so-called shortcuts. And in fact, there are plenty of opportunities for learning shortcut in medical images. So for example, in this paper published a couple of years ago by Digray et al., they showed that the model that is designed to detect COVID-19 from the images may focus on spurious hospital markers that are on an X-ray rather than looking at the medical images. So what would be equivalent of that in our example that I showed you earlier? In fact, if you show these images to any radiologist and ask them to distinguish between positive set and a negative set, they will probably come back with the same answer, that the anatomy itself is a clue of distinguishing positive set from the negative set. And as a result, if you train a self-supervised approach, constructing the data and set up a problem this way, the model will learn anatomy, which is uninteresting rather than subtle anatomical changes that are representative of the disease. So, and in fact, we show that self-supervised approach can be quite vulnerable to learning shortcuts. Let me illustrate this with an example. Let's say that you want to design a self-supervised approach that on this toy example, that is supposed to learn all of these latent variables of this toy example, including shape, color, and texture in an unsupervised fashion. Our colleagues in MIT, Sarah's group and my group showed that in this paper that's published in Europe last year, that info and CE loss may miss some of the important features of the latent, some latent variables of this data. So there are formal statement in paper, but informal statement of the main theorem in this paper says that based on the local minimum that the model converge on, you will miss at least one or several of the latent factors if you completely train this in an unsupervised fashion. And in fact, to enforce an encoder to learn specific features, we should hold other features constant across the positive negative sample. So in this example that I'm showing here, the shape feature is fixed constant between anchor and the positive set, and we basically fix the shape features on a positive set, and the color and texture are varying across the other. So as a result, a contrastive learning and info and CE loss cannot use the shape as a contrast to distinguish between positive and negative sets. But the challenge is in self-supervised learning, we are not aware of this. But this also gives us a hint that if we know the shortcut that is used, we can use a technique that constructs a positive set and negatives in a specific way to block it. So in our example, basically, if we know the anatomy is a shortcut, we can use image registration to block the shortcut by enforcing all of the negative set that all come from the same anatomical location. So effectively, the image registration block the shortcut. So, but that solves part of the problem, because that basically gives us a way that we can learn anatomically sensitive features for each location while we are interested in a patient level representation. So to get the patient level representation, we model each patient as a graph where the nodes are anatomical representation and the edges are overlapping or vicinity of anatomical landmarks. And every patient, of course, has his or her own anatomy that are specific to that patient. And we use graph neural network, and more specifically GCN, to learn the global patient level representation. So we have and we train the entire network in an end-to-end fashion, that one part of the network focuses on anatomy, and another part of the network that collaborates with the other part learns the patient level representation. So let me show you some examples of this setup. So we evaluate our method on 3 levels. First, we compare our method with respect to self-supervised approach to see how well the features that we are extracted are comparable to the supervised approach. The second one, we see how generalizable it is to other metrics of the disease severity. And finally, we see how we can use these metrics to bootstrap the setting that does not have enough data set. So let's start with the first one. So we are going to compare our method with the several self-supervised approaches in the literature that are state-of-the-art in medical imaging. And we are going to use 2 measures of respiratory that are used clinically for diagnosis of the COPD as a target of the prediction. So these 2 metrics are forced expiratory volume in 1 second, amount of the air that the patient can exhale within 1 second forcefully, called FEV1, and the ratio of that to forced vital capacity. And the Y square shows the R square of the prediction, it's a regression task. And the horizontal line is a supervised approach that is directly trained to predict this specific task. Now, the closer the gap between the self-supervised approach and that supervised method basically indicates that we are extracting as much informative information as a supervised method, and we see that our method almost closed the gap to the 0. So, but how generalizable it is to other metrics of disease severity? In fact, that was our initial motivation. So, what would happen if we evaluate our representation on 2 other important metrics of the disease that are relevant to the respiratory, but they are not but the supervised method are not directly trained to predict that. So in this case, we don't expect the supervised method to be an upper bound. In this case, the bigger the gap is the better. And in fact, we see that many of the self-supervised approach actually outperform the supervised method that is not directly trained on. So because the supervised approach tend to extract very informative features on one direction that we show that is trained on. And our method, that is the last one, the pink one, has slightly higher gap compared to other self-supervised methods. Now, our original intent of designing such an approach was generalizability and gaining data efficiency. Now, we are interested to see if, for example, we train our network, our feature extractor for let's say COPD, but apply it on COVID-19 patient, which is not the same disease, but still the anatomy and the imaging are the same, how much we can bootstrap this setup. So in this case, we applied in a smaller data set, which is 1,100 CT scan of the COVID-19 patient. Our task is to predict the severity of the disease. And the severity is not only based on the images, but it's also based on the level of oxygen, heart rate, and the reading of the clinicians. So here is the gist of the result. So on a y-axis, you see the accuracy, and different bars represent different methods. So here, the take-home message from this graph is that due to small sample size, the supervised approach overfits and does not perform very well for this for predicting of the severity of disease. And several self-supervised approach, although they outperform the supervised method, but because they do not incorporate the context of the problem, they may suffer from the shortcut, may not have the very significant gap when it's applied outside of this data set domain. And the last three gaps, that last three bars represent the three different variants of our method, where we turn on and turn off different component of our model, for example, blocking the shortcut, the specific way that we construct the graph neural network. And we see that each of these design choices contribute positively to the prediction of the severity of COPD, like COVID-19, when the network is completely trained on a different data set, although it is on a lung and a CT image where the disease is completely different. But let me use this opportunity and switch the gear and talk about the second aim of this project. The question now is that we were able to construct the features that are very generalizable. Now the question is that if these features that are generalizable, are they also related to something about underlying causes of the disease? And in order to understand that, we should be able to relate these features that we have extracted from the disease to other biomarkers. For example, the measurements from the blood and the genetic measurement that we have from the patients. And we usually, to be more specific in this case, we want to answer this question. Is, for example, the destruction of the tissue that we see in the CT images are related, for example, to involvement of, let's say, immune system that you can measure using the blood samples? So to answer that, the very first question that before answering how they are related, we should answer if they are related. And so, to put it a little bit formally, we can view that as a two random variable, where let's say X is a measurement, these new features that we have extracted from the images, and Y is a measurement that, for example, we have from the blood, for example, specific markers in the blood that represent the involvement of the immune system. So basically, before we are asking anything else, we have to ask this question if they have anything to do with each other. And to answer this question formally, we usually put this question in a in the form of hypothesis testing. More rigorously, we want to see if we can reject the null hypothesis that these two random variables are independent. And we want to see the evidence in the data, how much of the support it provides to reject the null hypothesis. So, however, I'm sure many of you who have worked with the data set in clinical setting have seen scenarios like this, that we have only limited number of patients with both modalities, but you have plenty more of the patient that have at least one modality and the other modality is missing. And this is what we call as unpaired data set, because the other pair is missing. And I'm sure many of us have thought about that, well, this is the data set that we usually discard, and this is a very expensive data set. I wish there was a way that we can take advantage of it. And this is, in fact, a very common problem also in industry, because it's a very expensive data set to acquire that partially support this project. So in the following slide, I'm going to present a general idea that how we can take advantage of this data set that we usually discard. So the general idea is as follows. If I put the null hypothesis that I showed you in the previous slide, the null hypothesis, when we put it in a mathematical sense, is as follows, that the null hypothesis is the equivalent of writing the joint distribution as a multiplication of the marginals. And at the very least that the unpaired data set can help us is to provide better estimate of the marginals. So, and why is it important? Because if we can provide a better estimate of the marginals, we can have a better control of the type 1 error or false positive. And that's the very least that the unpaired data set that we usually discard can help us in rejecting these null hypotheses. So to be more specific, we extended a method called Hilbert-Schmidt independent criteria proposed by Gretton et al., where the finite sample estimator of the test statistic almost looked like this. I'm saying almost because there are some terms that are proportional to the inverse of the cube of the n, that I don't show it in this slide to avoid the visual clutter. But basically, the test statistic can be written as follows. That is basically the k is the kernel of for x, which is x in this case represent imaging, which is basically patient-patient similarity that we can compute it using the patient representation that we discussed a few minutes ago in a previous part of my talk. And similarly, L is a kernel of a patient-patient similarity using the other modality, for example, blood samples or genetic data. And H is just a constant matrix that does the centering. So if we view the K and L as a matrices, the solid line here represents the patient with both modalities, and a dashed line here represents the data set that have unpaired data set. So if we can stare a little bit at this test statistic, it's not difficult to see that the test statistic can be written as eigenvalues of the K and eigenvalues of L, and unpaired data set under the null hypothesis can help us to have a better estimate of the eigenvalues. I won't go through the detail, but that's basically the gist of the idea. We theoretically showed in this paper below that the type 1 error, which is about the false positive, reduces as you have unpaired data set. This is the data set that we typically discard. And in this formal statement, the formal statement in the paper, we showed basically that the design estimator is consistent and more unpaired data help us control better control of the false positive. And also in the second theorem, we showed that if we are willing to make an assumption that both X and Y live on so low dimensional manifold, we can even improve the power comparing the method to independent test method, classical HSeq, that discard the data set. And so basically says that under some assumption that is not strange, basically some smoothness in the data living on a manifold, even the power can be improved. The formal statement also in paper, so I'm happy to discuss it after the talk. So in the interest of time, let me let me provide a very brief explanation about the experiment that we performed. So the gist of experiment as follows. We basically look into two scenarios of simulation. In scenario number one, we simulated the case that these two modalities, X that represent images, Y that represent, let's say, the blood work, are independent from each other. So null hypothesis should not be rejected. So in this case, we are going to look into false positive. In the second scenario, the two modalities are related to each other, satisfying the low dimensional assumption of the second theorem. And in this case, we look into power of the test. So this is an example of the result. So in this example of the result, X-axis represents the number of unpaired data set that we are adding to the test, and a Y-axis the false positive, and the horizontal line is a 5%. That's usually the typical nominal line that we use to reject the null hypothesis. Of course, the method that does not use the unpaired data set does not change the behavior as you add more and more unpaired data set. And the two variants of our method, I did not really discuss the two variants, but they're basically based on the same assumption, slightly different hypothesis, slightly different assumptions, but the same idea. They both hover around the 5% nominal value. One is a slightly more conservative. The other one is goes slightly over the nominal value of the rejection of the null hypothesis. But the take-home message from this graph is that by adding more unpaired data set, you can have a good control of the false positive without blowing the false positive up. And that basically says that you can control the false positive very well. In the second scenario, we look into the cases that the two modalities are related. So the null hypothesis should be rejected. As a result, we are going to look into power. Again, Y-axis is the power. X-axis is the number of unpaired data set that we are adding to the experiment. So again, the method that does not take advantage of the unpaired data set does not change the power because it just ignores that data set. And the best that you can possibly achieve is the oracle showing you the data set that's missing. And the two variants of our method basically fill the gap between the very wasteful method, the blue line, and oracle that's best that you can possibly achieve. And it can provide a basically better method. Of course, we cannot achieve the performance of the oracle. Going back to real application that we have a measurement from the CT scan and the blood works that are related to the immune system. And based on the previous study, we know that the immune system is involved in COPD. And we know that the null hypothesis should be rejected, but we didn't have enough sample. Only like 60 samples has both image and the blood work. But we have thousands of more data set with only one modalities. So now in this case, because we know that the null hypothesis should be rejected based on the previous studies, based on the lab work. So now we are looking to minus log of the p-value. And as you see, by adding more and more unpaired data set, we have more and more evidence for rejecting the null hypothesis that otherwise would have been underpowered and the data set and the study would have been wasted. To summarize the first part of my talk, we showed in the first aim, I showed the data efficiency for learning. So how we can use the context of the data to learn features that are representative of the many metrics of the disease severity in a self-supervised fashion by incorporating the context and avoiding the shortcut that otherwise result in spurious features. We showed that such an approach can help to bootstrap studies that may not have enough data sets. In the second aim is about gaining data efficiency in a statistical inference. We showed that when the features are high dimensional, gaining power is even more challenging. So we have more data sets. So we need more data set, but we know that the data set is very expensive in the healthcare setting. So we show an approach that can help us to take advantage of the data set that we usually discard. So we showed an example in an independent test specifically. So if there is no question about the first part of my talk, I would like to switch gear and talk about the second part of my talk. Is there any question? Okay.
So far, no question in the chat. Kehan, maybe I ask a very fast question here,
Sure.
right? So even when you try to avoid the shortcuts, right, there are still augmentations that are applied to those patches. And I would like to understand a little better. In the natural images, we are aware of what type of augmentations are allowed, right? Mm-hmm. In the medical domain, what is the state of the current augmentations in the literature? And also, do they account for the variability between the different scanners?
Yeah, that's a very good question. I think there are still a lot of works to be done. For example, it actually depends a little bit on the type of modality. For example, in a CT scan, because the intensity values have a meaning, in my opinion, it's better not to play with the intensity. Do not apply the augmentation that change the intensity value too much. That is not the case about magnetic resonance imaging because the intensity value does not have a meaning. It's all about contrast. So to answer the question, the type of the augmentation depends on the modality. And if it is CT, I personally prefer not to change the intensity values too much because it influenced what the model will learn. Rotation and changing the scale, those are okay. So to answer the second question that you said about change of a scanner, so far I haven't seen any method that apply augmentation that mimics the change of the scanner so far, but that's very interesting direction to go.
Thank you. Thank you.
So now let me switch gear and talk about the second part of the talk, which is about explainability. So in the context of, in many applications of the machine learning healthcare, it is very important to be able to communicate the reason that the black box is making a specific decision, not only to gain a trust, but also in order to identify the sources of the signal in the image that the model may latch on that may be spurious, because most of these models are designed by machine learners that are not necessarily expert in clinical domain. So this is the project that is done by my PhD student that is recently graduated. I'm really, she's my first graduate student. I'm really proud of her work. And our collaborator in radiology department, Stefan Wallace, and my former postdoc, Brian Pollack, and in collaboration with my colleagues in CMU, Motahari Islami, in human-computer interface, because we realized at the end of this project that at the end of the day, if we want to care about the real application of this method, the interface with human is very important. And this basically needs a whole different type of expertise that is beyond our scopes. And this is why we collaborated with Motahari. Well, perhaps one of the most common approaches for model explanation in computer vision is saliency map method like GradCam. I'm sure many of you guys are familiar with it. That basically focuses, that basically identify regions of the image that contribute the most to the output of the black box, let's say, classification. However, application of such a method on medical imaging is quite problematic. In some cases, for example, when abnormality is supposed to be localized, the GradCam or saliency approach may result in very diffuse result that makes the explanation very difficult. In some other cases, for two diseases, the explanation might look very similar to each other. That makes the explanation of this very challenging, because they say that, well, regardless of the output, it's the same explanation. So in fact, every time that we show it to our radiologist collaborator, he said, get this heat map off the image. I want to see what is inside of the image. And he always come back with the same question. What should change in the image that flips the decision of your deep learning method? So what he said basically made us think a little bit deeper about this notion of explainability. So he was more interested in why question rather than where question. That is, where question is mostly answered by saliency map or method like GradCam, but they're not able to answer why question. So philosophically speaking, this is more like a counterfactual explanation. So we came up with this idea that, let's say that we have a classifier F, that whenever we input an image, it produces an output probability of, let's say, certain disease, let's say cardiomegaly. And this is the factual output of this black box. What if we view this spectrum of the output as a knob, that our colleague can play with this knob, so that he can play with this knob and move it, let's say, by delta, and then ask what changes in the image should create this desired counterfactual outcome. So the goal of so-called explainer function that here I'm showed in this green box is to generate another image that if I plug it back to the image, it generates the expected output, as if this knob can exaggerate or de-exaggerate the effect of the outcome. So explanation like this depends, of course, on input X, amount of the change delta, and the output, and of course, the black box F. So what would the criteria that such a function should satisfy? Of course, the results should be realistic. Should basically, if you view the data lives on a manifold, the counterfactual image should also lives on the same manifold. It should be compatible with this black box, meaning that if I play with this knob, it should be sensitive with the location of this knob, and it should be self-consistent, meaning that if I move this knob a little bit forward and then redo the whole explanation with respect to that and move it backward, it produces the same image. So I won't go through the detail of how we designed this, but effectively, the way that we think about this is that we are binning basically the output probability into quantiles. The goal of the explanation is to generate samples from conditional distribution, where the condition is the index of this quantile. So we can do this with some modification with the conditional generative adversarial network, CGAN. I won't go through the detail of that, the details of this ICLR paper that's published a couple of years ago. But basically, as these bins become smaller and smaller, the support of this conditional distribution overlaps more and more with each other. And there are challenges corresponding to that. And we addressed that in that paper and some papers that followed up with that. But basically, the problem can be viewed as a conditional distribution estimation. So I won't go through the detail, but in interest of time, because there's not that much time left, let me go through the evaluation. Let me show you just some qualitative evaluation, and I'll explain the quantitative evaluation and the challenges corresponding to that. So for the sake of example, let's say that you have a classifier that detects a person in the image is smiling or not. The person on the top is not smiling, the person on the bottom is smiling. So playing with this knob is amount to traverse the spectrum of a smiling or not. This is just to get an idea of like how in general it works on a toy example. So we applied it on two conditions. One is called cardiomegaly, which is enlargement of the heart, and playing with this knob amounts to enlarging or like making the size of the heart bigger or smaller. For another condition called pleural effusion, which is about accumulation of the fluid on the lung, you see that at the corner of the lung, because the accumulation of the fluid, the sharp angle become curve-like. So like this is what we call like blunting effect. That like the sharp angle that you see on one end of the spectrum become blunt or curve-like because of the accumulation of the. So that is on a visual explanation. So, but now the challenge is that, okay, so visually it makes sense, but how can we quantitatively evaluate? So we quantitatively evaluate this method on three levels. On the first level, we said that we have a set of criteria for this explanation that we designed it. So it should satisfy those criteria. The second one is that the counterfactual explanation should be consistent with the clinical definition of the disease that we did not use during our training. And the third one, as I mentioned earlier, is a human-computer interface. So if many of the explainability methods are basically boiled down to machine learning expert explaining things to another machine learning expert. Is this method useful to explaining this to non-machine learning expert, to basically a radiologist? So I'm going to go through the different ways of evaluating this method. So the first criteria that we have was consistency of the black box. So on the x-axis, you see the initial factual value plus the delta that we want to use it versus x delta, which is the counterfactual image generated after we plug that in. And if it is consistent with the classifier, these curves should follow the 45-degree angle. So we are showing the result for three conditions: cardiomegaly, pleural effusion, and edema, and different curves represent the different population. For example, the yellow one are the ones that are initially diagnosed as a high cardiomegaly, and the bluish one are the one, dark blue, are the one that appear normal. And basically, this curve shows that regardless of the initial state of the patient, they all of them almost fall like 45-degree as expected. In order to see how consistent it is with the clinical definition of the disease, we look into clinical literature. So for cardiomegaly, the way that the doctors diagnose is that they measure the ratio of the size of the heart versus the size of the lung and compute a ratio called cardiothoracic ratio, CTR. So we said that, okay, so if this is consistent with the clinical definition, if every time that we create this segmentation, this counterfactual image, we can segment the lung, we can segment the heart and compute this ratio. And if this is consistent, this delta, this change in a CTR value should be significant with respect to previous one. And this basically graph shows that statistically it contributes significantly to the change of the CTR value. For the patients that are at the beginning look normal, it reduces the CTR value. For the images that look abnormal, it increases the CTR value that is consistent with the clinical definition of the cardiomegaly. For pleural effusion, as I mentioned earlier, because of the accumulation of the fluid, the area of the lung become blunt shape of this curve shape. So we train a post hoc detector and applied our counterfactual images and compute a score that we call it castrophenic recess. It's basically a number of times that our detector that detects the blunting effect turns on the image. And we see that for the images that are normal, it statistically fires with a higher rate, this detector, and fires less on the images that are abnormal. But these are on quantitative evaluation of the explanation based on clinical definition of the disease, how useful this explanation is. So we run a survey in collaboration with Motahare. We designed a survey with the radiologists involved, so that we blind the method. We ask several questions. I'm going to go through two of these questions. The goal of this survey was to run a study to see how useful this explanation is to gain a trust for radiologists. So we compare our method with no explanation, so providing only the input image and output prediction of the black box, saliency map, cycle GAN, which is probably a natural competitor to our method, and the fourth method, we call it PC, progressive counterfactual explainer. And every time we show them the output, counterfactual image, and ask a question about, ask several questions that I show two of them to you in the following. Cycle GAN, in cycle GAN, we go back and forth between two ends of the spectrum, and our method basically goes through the entire spectrum, which is just like my bad rendering of the way that we show them the questionnaire. So in the first question is about understandability, how this approach can help them understand the way that the AI is making decision. So the blue is the y-axis is percentage of the response that they agree with the AI method. So the PCE is our method, cycle GAN, saliency maps, and based on which is no explanation, and we show that significantly it improves with respect to previous explanation method. The second approach is about helpfulness, how which explanation basically helped them the most in understanding the assessment of the AI. So because if you want to basically use this method in clinically, we want to see how helpful it is for clinicians. And again, this specific way of explaining by gradually going from back and forth to the spectrum allows us to have a better understanding of the AI system. Now, let me very briefly talk about what this can be useful for. So currently, we have not opened the black box. It's basically create a visual explanation that basically continuously traverses the spectrum of the output, but does not tell us what is going on inside of this black box. So let me tell you a little bit about this ongoing research that's part of that published last year. And the other part is like under review. So basically, the general idea is as follows. So I'm going to borrow some terminology from causal inference to explain this idea. Our method basically allows to intervene in the input image, which indirectly intervene in the activation of the internal neuron inside of the black box. If we map the pattern of the activation of the medical concept that are usually available in the radiology report that comes with the images, we can use the method from causal inference, specifically mediation analysis, to analyze and to identify the neurons internal neurons of the black box that influence the output and explain the decision-making in a radiology term, in radiology language, exploiting the radiology report. In that way, we can provide a clinical provide an explanation that is closer to clinical understanding of the disease beyond just visual explanation, and effectively opening the black box and identifying the part of the black box that are responsible for that. And we are able to create local explanation that looks like this. For example, we can say that there are part of the neurons that are responsible for, let's say, pleural effusion, vascular prominence, that is the term specifically known for radiologists, and so on and so forth. And locally, the decision-making of the black box can be explained in the radiology term in a hierarchical manner. And what is that useful? By intervening in the neurons that are responsible for undesirable properties such as bias, we can fix the black box. Effectively, we can put the explainer method and black box in a self loop so that we can fix so that we can fix undesirable properties of pre-trained networks. In this paper, that again the following paper is under review, is that we show that by making this loop between explainer and the black box, we are able to fix a black box by a little bit adjustment and make it less overconfidence, because for many of these black boxes, when they are applied, it's very essential for us to have a better estimate of uncertainty, and this loop between explanation and black box can help us to achieve that properties. I didn't go through the detail of that in the interest of time, but let me summarize the last part of my talk. We develop a method for counterfactual visual explanation, and that effectively increase or reduce the effect of the disease, and use the visual explanation to convey the way that the black box makes a decision. Our experiment shows that the counterfactual explanation is consistent with the clinical definition of the disease, and our surveys showed that is more helpful than the current method for model explanation. We are excited about the progress of this research and bringing more idea from causal inference in order to be able to open the black box and provide the fix to undesirable properties of the black box. So let me summarize my talk. Over the past 10 years, question in current AI field has been dominated by the need from tech giants such as Google, Apple, and so on. We have learned a lot through many systems that are, many questions that are basically the question that the tech industry were interested in, such as self-driving car translation, and we have learned a lot. But many of those techniques that we have already developed in the past decade may not directly be applied for application of the AI in healthcare. So I believe that the next trend will be decided by the real application, by the real domain application, which drives whole new set of questions that needs whole different way of thinking and the theoretical and practical development. Of course, there's a significant overlap between the techniques that we developed earlier and the method that will be developed by the community over the next 10 years. But I'm encouraging everyone to think about the application of the method that they're going to apply on, because there are plenty of work to be done. On that note, I would like to thank wonderful members of my group. I'm so honored and lucky to have them on board. They have done all of the hard works, and basically I did cheerleading for them. And many thanks to my collaborators from University of Pittsburgh, MIT, CMU, Melbourne University, and Northeastern, and Harvard, who made the project grounded. And finally, I would like to acknowledge funding from NIH, NSF, SAP, and Pfizer that help us to work on this problem. Thank you very much.
Well, thank you so much for the fascinating talk, Kayhan. Let's unmute and thank our speaker.
Thank you.
Thank you.
Thank you.
Thank you.
Questions. So I see that Lance had 2 questions in the chat. So Lance, if you unmute and ask, that would be perfect.
Yeah. Hi, Professor. Thank you for the interesting talk.
Sure.
Yeah. I have a question mainly for the first part of the talk. So first is about the image augmentation. You said like a rotation, and you show also example of rotation. I'm just wondering, like for those images, they seem to have inherent directions, like the up and the down. I don't know if would this hurt like the performance or something?
Yeah, that's very important. That's very interesting question. Yes, that is actually very important things that the vanilla rotation won't work. So, so there are a couple of things that we experiment with. So we apply the rotation in a physical domain, right? Because like you're using a patch that focuses on a small area of the image. If you apply the rotation, the classical way that we apply rotation in vision, you introduce like a black area into areas that goes outside of the image. But you apply the rotation on a physical domain and repatch, you don't have this problem. In order to avoid that, we don't flip the direction, we limit the amount of rotation, because at the end of the day, this is an easy pre-processing things to be done. Like you can always make sure that all of the images on a CT, there are, for example, head first I won't go through the detail of that, but it's basically the so-called nifty format is a specific imaging format. We can easily perform reorientation that all of them have the same orientation. So you don't really, as long as so for example, you are not supposed to do mirroring, right? We don't do mirroring because mirroring is the equivalent of changing the meta information in nifty images. We didn't do that. So we were careful about what kind of rotation. We limit the amount of rotation so that it is consistent with the way that you may see the patient. For example, imagine a patient may move a little bit, but it's not going to be upside down. Or the patient in scanner not going to be like this. The scanner patient goes through that. So we limit the amount of rotation. What was the other question that you said?
Oh, the other question is about contrastive learning. You said you constructed graphs from those CT images. I'm thinking like for CTs, there are different slices, right? So different slide may give you a different graph. So which slice do you select? Okay.
So we did so let me go back. We didn't do that in a slice manner. We did it volumetrically. So we did several experiments. There is a longer version of this that is not out yet. So we construct our graph neural network volumetrically. So we are not focused on a slice. We create a volumetric image. We did experiments with a slice. We saw that the shortcut is very salient because effectively the contrastive learning can read the slice number from the whole graph. So we decided not to go with the slice level. So there is a disadvantage to this, because when you do volumetric convolution, and also you have to construct an entire image. So you're effectively your volumetric from memory point of view, you're using the entire image because for one patch you're using one area of the image volumetrically, and the patches are overlapping. You're actually using more memory than feeding the entire image to. So the disadvantage is that your batch size reduces, but you don't have the model using slice number as a shortcut. So we experiment with a couple of that. We realized that constructing this this graph neural network volumetrically. So it's there's no corresponding with the slice. It's just the entire volumetric. Did I answer the question?
Yeah. Thank you.
Any other questions from the audience?
Hi, Professor. I'm Brian. I have a quick question about the PC method you mentioned. So I wonder if that method generalizes to, multi-class problems.
So, so let me go back. If I find my mouse to monitors. Okay, so it does. Okay, so let me bring it up. So I create an example here in a binary classification for illustrative purposes. So the problem that we have was multi-label, right? So because each image can have multiple conditions at the same time, and it is easily, in fact, in a paper that we had in ICLR and a later follow-up paper that you can find in the archive, it is multi-label classification. Talking about multi-class, we thought about it and we created one versus all multi-class classification.
Okay. Yeah.
So the issue here is that, okay, so you can do pairwise and you can do one versus all.
Right.
If you do pairwise, you have a problem of scaling to multiple classes. So if the number of classes, the n choose 2, right? So basically one versus all is easier. But then the explanation, so basically if it's one versus all, you go from one end of the spectrum to which one, right? Which other classes? So there's always challenge between, okay, computationally one is easier, conceptually is hard.
Okay, yeah, that makes a lot of sense. Thank you. And I actually have another question. Sure. So for the next part about opening up the black box, you
Yeah,
mentioned,
yeah.
you kind of investigate a causal relationship between neurons and outcomes. I wonder how exactly did you do that? Like,
Okay.
I think it's very similar. It's more like label these individual neurons.
So yes, exactly. Yes, exactly. So let me see if I can find this slide. Do you see that?
Yeah.
Okay, so yes, exactly that. So think about it this way. So you have this augmentation.
Mm-hmm.
So you have this augmentation. You have one end of the spectrum. You have other end of the spectrum. You can create factual image and create counterfactual image. Look at the activation of the neurons, right? You can store the activation of the neuron and then look at the presence of the term in the radiology report, and you can label the neurons, right?
Right.
So now, if you are labeling the neuron, the question is that, is it just correlated with the presence of that term, or is it causing that? So you need to compute so-called, let's see if I have it here. So you need to basically ask this question. So if these are activation of the neurons that are this, let's say each of these the color represents presence of a specific term in the radiology report, right? So you want to see that if activation of these neurons are causally changing the output, or it is just in a way, it's just like correlated with the output.
Right.
So using the idea from mediation analysis, you can think of it this way. You can like as if that you are associating a pill to a patient. Let's say that the pill is the image, right? And the output of the classifier is the outcome, right? The mediator is the effect of these neurons.
Right.
One effect, so the treatment can have a direct effect, not going through those neurons, and have an indirect effect. You follow what I'm saying?
Right. Yeah.
So, but this is easy to compute because you can see that like how many times the pattern. So basically, it's just computing a ratio, because you can associate different treatments and look at the output of the value of the neurons and see that how many times this activation of neurons are changing the output in a factual sense. But yes, to answer your question, exactly. So we changed our input, we measured the activation of the neuron, and then we basically train a classifier between activation of neurons and the presence of the term in the radiology report.
Okay. Yeah. Thanks for the explanation. Actually, sorry, I'm taking
No problem.
more time, but I have two follow-up questions actually. Sure. So this black box you mentioned is a generative model, or it's a classifier?
It's a classifier in this case.
It's a classifier. Okay.
Because it's the input is an image, output some prediction value, right?
Okay.
Yeah.
Gotcha. Yeah, and because there are so many neurons in a deep convolutional neural network, like did you have radiologists have look at each of them, or?
Well, the way that so many of these images come with the radiology report, right?
Okay.
So the report is written by radiologists.
Okay. Yeah.
At the end, when we associated neurons with the terms, we show that to radiologists. But to make that association, it's just you have a report already. The report is written by radiologists.
Okay.
Right. So, but I have to say one thing about this is that, because are you familiar with the concept explanation, like basic concept-based method for explanation?
Not really.
It's like basically you can think of it this way. It's like there's not really one neuron that is associated with one term. It's like a set of neurons. Right. So equivalent. So at the end of the day, we are not really identifying one neuron. We are identifying a set of neurons that are activated with that pattern. So it's not. I'm simplifying in explanation. In a paper, the way that we did it was that we look at the activation of the neuron and say that what's the sparsest number of the neurons that are correlated with the presence of the term. So that is like, it's like a coloring of set of neurons.
Okay, gotcha.
Because one neuron is never enough for explaining one concept.
Right, gotcha. All right, that makes a lot of sense. Thank you.
So, okay, while we're on the topic, in PC and in generating the counterfactual, so I was wondering if the classifier like has to be normalized for uncertainty, like in the uncertainty quantification, right? Like you normalize the output of the networks to align them with the actual uncertainty of right. So that 45-degree lines that we were getting, are they actually meaningful in the sense that is the classifier already normalized for uncertainty or not?
So there are two aspects to this. So what you are referring probably is calibration.
Right.
So the 45, regardless of whether your classifier is calibrated or not calibrated, so the 45, if the classifier is calibrated, the bin of the histogram versus the number of the times that, so for example, if you're 70 times, you associated the value of 70%, between 70% and 75%, 72% and half of those should have a true label value. It's like that's a, like, you know, what calibration is about. That's 45 degree. If it's your classifier is calibrated, that should be 45 degree. That 45-degree angle, which if the classifier is calibrated, that's 45 degree, is different than 45 degree that I'm mentioning here, regardless of the whether your classifier is. Okay, let me bring this result.
Right. Just to clarify, I think I understand the difference between these two. But like,
but we do calibrate it.
Okay, if you don't calibrate it, then your explainer is going to be also biased, kind of, right?
Exactly. Yeah. And this is what we try to show in this part. Like, I don't think so. Here, like, basically, we show that, okay, let's say that you are given a classifier that is not calibrated, right? So this, and the calibration plot is not 45 degree. Can we use an explanation that is basically explaining something is uncalibrated and put them in a loop and adjust the weights a little bit? Can we fix this lack of calibration? We showed in this paper that it does help. So, but it helps more in terms of like identifying, basically providing confidence about the sample. So because effectively what this method does is that if you have two samples on a two, let's say that in very like this is hard to do this in Zoom, but let's say that you have this part is class 1 and this is class 2, right? And there's a boundary between them. The explanation is equivalent of traversing from one sample from one side of the spectrum to another one. Okay, so effectively, if you create an augmentation based on this classification, put it back and retrain a little bit, you can make this edge between these two classes smoother. Do you follow what I'm saying?
Yeah, absolutely, absolutely. Yes, it's very much like adversarial training, right? Like similar concept to adversarial training, but like in a very different domain, right?
Except that your augmentation is coming from your same black box.
Right. Yeah. Although like I envision that like this. I can imagine that the training this is not as straightforward. You have again in right. Okay. Yeah. Cool.
So it's not a cheap fix. It's not. Right. Is it an expensive fix? Is it the best fix? Probably not.
It's still fascinating. Yeah. Thank you. Any other questions?
So one question that I could ask was that in one of the earlier works, I think it was around slide 36 or so, that you had showed the comparison of your method, which was based solely on the two self-supervised loss terms in relation to this.
Are you talking about this one, 36?
Yes. Mm-hmm.
Okay. Yep.
So here, this dotted line you had mentioned is the supervised training. And I was wondering, and then you had shown that on I think a smaller data set, the supervised can be prone to the overfitting, and it would go beyond this line. And so what would happen if, rather than just having the two self-supervised loss terms, but if you also integrated the supervised, like task specific here?
Yeah, so in this case, like we were trying to follow the tradition of the way that the literature of the self-supervised learning evaluate their methods, where they say that, okay, we are assuming that the self-supervised method does not have any access to the supervised information, to the task that you are interested in. And you're training a self-supervised approach and using the last layer for doing like simple regression. Because if those are informative information, you should be as good as a method that is directly trained on that supervised. So probably if you would have include some supervised approach into the loss function, in addition to contrastive loss, these might have improved. But I'm not sure that would be in the detriment of the other metrics that we were interested in. Because if you remember, we were also interested in going beyond the metric of, beyond the features that supervised method is trained on, right? Because eventually we want to see that if it is very generic features, we should apply it on something that we never see, the task that we've never seen before. Like, for example, like if you give me the new blood work, I've never seen it before, so it should be able to be related to that. But so basically the goal was to see for the metrics that we can train the network on, we have enough data set, how close that we can get the supervised approach, and how generalizable it is for the one that we don't have access to. Like, for example, it shows up in the future.
Okay, so here, as compared to using it as a pre-training, just as
exactly.
a fixed representation and then directly reusing. Okay, yeah, and really great work with the explainability. I really
thank you.
So, thanks.
Okay, so we are already 15 minutes over our time. Thank you so much again, Kayhan.
Thank you very much for inviting.
Very good talk, inspiring. Yeah, we really appreciate you.
Thank you very much for inviting.
Absolutely.
Honored to be here.
Great.
Hope to see you next time in person.
Absolutely, absolutely. Yes, have a great one.
You too. Bye.
Thank you.